Hello again. Guess who is back? Well, you don't need to guess, it's Demonari here. I've been away for a very long time, but that was due to some IRL issues. Anyways, let's continue with whatever nonsense I have going on here. This project is a custom allocator, specifically a debug allocator. A lot of C and C++ programmers, and especially Rust programmers, keep saying that they leak memory when they are coding in C and C++, and they have overflow and underflow issues and accessing after free and all of that nonsense. There is a very simple solution to all of that. If you don't want a simple solution and you just want to get bashed in the head by the runtime or the compiler, you have your debug allocators. What does debug allocators do? They just tell you if you did something wrong. Let's do some basic code review of what's wrong in this code. We allocate a new string of 100 bytes. Then we have another string after that of 200 bytes. This is completely fine. Then we do an str copy. We copy the string text. But if you hover over it, you see 260 bytes, but we allocated only 100. 260 is quite a bit more. After we do this, we memory overflow. We corrupt the next block. But we only catch it when we try to verify or when we try to free the block. Not only that, we also didn't free new string. We just overrode it here. It would also tell us that. Then we make the second allocator. So we allocate a string of 50 bytes, 32 bytes, and 22. Then we do a free with double underscore. Double underscore is my macro for just freeing the data. As you can see, it also inputs the line and file. And same here, you always want to pass the line and file, and this is why those macros are there. Here, we are trying to free, but with the wrong allocator. We can just do free like that, and it would automatically detect the allocator unless the data is corrupted. We have this free, which is a double underscore instead of the normal one, that uses the correct allocator to free new string 3. After that, we try to free the string again, but we will get a warning that it's freed already. And then we do a free on this string that was already set to null. Then we should do this and get allocator 2 is completely fine. And when we destroy it, it would tell us, well, data is not freed, and it would tell us also what data is not freed. Same here, data not freed and block is corrupted. Let's start and see the actual result. Magic word test failed, no allocator provided, possible data corruption, no memory freed. Calling from here. Calling from tells you what line in code the error happened at. Not only that, but you can also add breakpoints inside the allocator to basically break whenever something like that happens. But I don't really care. I know that the error happened here. It tells me what the error that happened tells me here. Allocated at, we can't really read it because it's a magic word test failed, so possible data corruption happened, and we cannot dereference the file name and line from there. Then we start allocator verify, memory overflowed, possible corruption here in new string. And then we look and we see, oh wait, I did str copy in new string with no actual stuff. So maybe it failed because of that. And this is memory overflowed. After that, it can be that the memory just overflowed by a little bit and it didn't corrupt the next block. But when we get to the next block, we see magic word test failed, possible data corruption. Data corruption possibly caused by block allocated at here. And critical error, terminating test, ending allocator verify test. I can do a recovery stuff and see, well, here there was something there, and just merge the chunks and correct the allocator from that. But this is just a basic debug allocator. It's not supposed to fix problems and stuff like that. It just tells you you fucked up and you need to fix your code. Next is the attempting to free memory not owned by allocator. No memory freed. It's telling you, well, you try to free this, but it doesn't belong to this allocator. Allocated at here. And then you can see, well, I used allocator 2. I didn't use the regular allocator, I used allocator 2. I should fix this. Then, after that, we call free new string. Now, this also just calls this macro and then sets x to null, so that we don't leave new string as something that can be messed with. Then we try to double free, because we use the double underscore here, so it doesn't set it to null. So we can test what happened if for some reason we saved the pointer somewhere else and then we try to free it again. Already freed, no memory freed. Calling from, and it tells us it was allocated here, so that you can see, well, it was allocated to this value. Maybe check this value, track it, and see if you did something stupid with it. And then attempted to free null. Here, after new string was already set to null by this macro, this line, we try to free it, but we try to free null and nothing happened. Then we do the verify. This allocator has nothing wrong with it in the verify test because everything is okay. It just says starting verify test, ending verify test, then destroying allocator 2. Okay, so starting allocator verify test, verify and leak test. This is just a verify test, and when we destroy it, we call it with verify and leak. Leak found at block, allocated here. We allocated this and we didn't free it. And tell us what's the data inside the block. And of course, ending allocator verify and leak test. Everything outside of this leak was completely fine. Then allocator destroyed. Now we destroy the second allocator. Memory overflowed in here, new string. We remember that. Then block data. Because we overflowed memory and didn't release it, it had 3 errors. Overflow memory, memory corruption, and memory leak. Then we get the critical error, ending allocator verify and leak test, and then we destroy the allocator. The very important thing is that this entire program can run and finish its process without crashing. Everything works as intended, and all of the fails are soft fails that allow us to continue processing the code and fail gracefully with error messages and logging everything. So this is the allocator. If you want to keep everything outputting specifically to your log file, SafeFree also receives the allocator, so even if there is a memory corruption or some other nonsense, it still outputs everything properly. If you just output everything to stderr anyways, you can use those, and this is the demonstration of what it does. What is this allocator? Of course, stddef and stdio. Why stdio? Stdio because we have a log file. stddef is because we have a size t. And of course, this is written as C and C++ compatible, meaning it's perfectly compilable in both C and C++. Here we have all of the allocator function. If you want to allocate the allocator on the heap, because we don't have a prepared buffer for it, we use that. It tells the allocator to allocate itself on the heap and then return us an allocator pointer. And also when we call allocator destroy, it would free the allocated memory. When we use that, it wouldn't free it because it assumes that it's not something that the allocator is responsible for. The allocator is responsible for freeing its memory when it is the one that allocated the memory. This creates the allocator in either heap or in a specific buffer and returns a pointer. Then allocator destroy. Allocator destroy destroys the allocator created here. So allocator defrags continuous freed blocks, and malloc basically searches for the first free block that has the size and returns null if there is no available block. On the way, it will merge all continuous freed block it finds. What does malloc take? Malloc takes the allocator, takes the size, and also the line and the file that it is called from. This is very important because this is what tells us where the error happened. It also exists in free and free safe. Then the allocator verify. This is the verification test. Then allocator errors. Here we have an enum that tells us what allocator issues can happen. Okay, we free null, allocator null, not owner, not allocated, magic word corrupted, and memory overflow. Then the defines for kilobyte, megabyte, and gigabyte. I know those are not actually the correct sizes for those, but they should be that in my heart, so fuck it. Then we have those macros. Of course, the _d is because this is a debug allocator. It's not a release version hyper-optimized allocator. It's there to debug issues. If you want a good allocator, use something that someone who actually knows how to create good allocators does. And those allocators are normally running in kernel space. So no user space programs. I'm here for user space programs. I'm not here for kernel space stuff. Let's go over the implementation detail. Magic word. Magic word is a specific set number that is very unlikely to happen naturally. So this is my choice here. You can guess why. Chunk size. I want my data to be 512 bit aligned. This can be changed. It doesn't have to be specifically that chunk size, but yeah. So magic word count. Magic word count is in the allocator to make data specifically 64 bytes aligned. Inside the data cell, we have a magic word at the start and a magic word at the end. So overflow and underflow would always cause corruption. The allocator address is stored here. This is how we get the allocator. Allocation size is the actual size in memory of the allocation after the data cell. Line source is how we store the line, and file source is how we store the file. Is allocated. Basically tells us if the data cell after this header is an allocated cell, a freed cell, or is a final cell. And then the real size. Real size tells us how much of that chunk we store the real size, and then we can check if the user overflowed from that chunk. Here is the allocator, allocator address, allocator size, basically how much data is in data, the log file, and a flag to tell us is it allocated on the heap. Here, if allocator is malloced, free. So allocate on heap. Allocate on heap basically does this, aligns the size to chunk size. It truncates the size to chunk size. Then malloc that truncated size into a buffer. Call allocator init in buffer with the buffer and the truncated size and the log file. If no allocator was created, then we test if the log file is null. If it's not, we use sderr. Then we check if buffer. Then we say call to allocator init buffer failed, free in allocation. Otherwise, it probably failed because buffer was null. Then we don't need to free it. And the allocator init buffer should have probably told us what was wrong anyway, so we don't need to actually output anything. Then, if it wasn't null, if we got a real allocator, the init actually succeeded, we set the isMalloced to true, then return alloc. Okay, so what happens when we do use the allocator init in buffer? We first test if the log file is null. If it's null, we set it to stderr. That makes a valid log file. Then truncate the size. If null, then buffer provided is null and we return null. Then we modify the buffer to an allocator pointer and say, okay, this is an allocator. Then if minimum size requirement is not met, we output the buffer size not meeting minimum requirement, LU, provided only this much. Minimum size requirement size, so we actually know that there is an issue. Fail because not enough data. Then we initialize the allocator. Allocator address is alloc. Allocator size is size minus offset of data. Log file output is log file output. Is malloc false? Because we assume that we are allocating in buffer, and if not, it would set it later. Then we set the magic words to magic word, and then we take the initial address and the final address for data blocks, and we init the data cell here and here. The final one is with size 0, and the initial one is with allocator size minus the size of the two cell headers that we are creating, initial data and final data, that both are in here and in here. And of course we pass line and file in the arrows so that we can see this happens here and this happens here, okay? And after we initialize the data cells, we return the allocator destroyed. First, we verify the allocator. It just tests that a few sanity things are properly set. If the status of the allocator is not okay, we return the status. And then our current log is the allocator log file output. Destroying allocator verified with test leaks set to 1. Then if it is mallocked, we free, and then allocator destroyed. Then we return the status of the allocator verify. Allocator defrag, basically verify the allocator, like pretty much anything in here. If the allocator is not okay, it returns a status. Then we start with the first cell, and the previous cell is null. While the current cell is not the final one, previous is the current cell, and the current cell is the next. Okay, and then if current is not null, previous is not null, and then both current and previous are not allocated, we can merge current with previous and set previous to null. And next time that we go, it would become the previous, the current would be the next from the merged cell. If the following one is also not allocated, we will merge them again and again and again until we find an allocated cell. When we find an allocated cell or a final cell, we stop. This is how defragmentation worked. It just merges the cells until everything is fine. What does malloc does? Allocator would verify. If size is 0, please don't try to allocate no bytes. If the size is bigger than the allocator size, what the fuck? And if it couldn't find anything of this size, it would also tell you. And current and previous, same as before, until it is reaching the final cell. It verifies the cell. If current is allocated and current is not allocated and allocation size is bigger than size, then we try to split. If we can't split because it's not enough to split, we just say, okay, we take the entire block. Test becomes the entire current block. Real size becomes the size that we requested, and we zero trail. Then we verify the cell. This is just for me to test if split data cell or zero trail caused any issue. Is allocated is now true. File source is the file provided here, and line is line. Then out is test plus basically offsetted all the way to the next data cell or the start of the data inside that allocation, and then we return it. If we didn't find, previous become the current cell become the next cell, and we try to merge 3 cells. If after all of that nothing happened, then we say that we failed to allocate and we return a null. But normally we just return here this data. Now free. Let's start with the safe free first. Safe free. Verify the allocator. If the allocator is not okay, it returns a status. If memory is null, attempted to free null, no memory freed, calling from, tells you where it is. Okay, and then cell is the memory, but subtracted once, then allocator free cell, which basically just does all of the tests for us without the allocator, just underscore free underscore d. Memory is null, default output, no memory freed, calling from, of course, yes, and then cell, magic word failed. Magic word failed means that we cannot get the allocator, so we return magic word corrupted, and of course we default to outputting to stdl. After we succeeded both of those tests, we take cell allocator, cell, line, and file. Allocator free cell, verify the allocator again, because maybe we got there from here that doesn't verify the allocator. So verify the allocator, get the error log file, then test magic word for the allocator. If magic word failed, we say magic word corrupted and tell where we are calling from. We get the cell address and the allocator address, and we test as basically size t as a number. If the cell address is smaller than the start of data or bigger than the address of the final cell, then we are attempting to free memory that is not owned by the allocator. The allocator knows the bounds of the memory allocated here. Basically, this actually just does the plus allocator offset minus cell size, which are the same. So I just don't write any of them. Then we output this and allocator error not owner. If it's not allocated, attempting to free memory already freed, return not allocator. Then we do cell is allocated equal false. After all of those, we do test 0, testing the memory after the allocation. The test 0 is failing memory overflow, and there is a possible corruption, and tell us all of the data. And then we return OK. Here, I can actually add term int l memory overflow so that it's consistent with other issues. Allocator verify. Allocator verify basically does all of the tests. This does all of the verification of the allocator struct itself, which is testing magic word. Address of allocator is not allocator. This is also a corrupt, same as magic word test, but this tests in another location, basically just a sanity check. Here, allocator verify. So current and previous, of course, back into the same logic. Starting allocator verify test, and this is basically just the 2 messages, one for the verify test and one for the verify and leak. While it is not the final block, we verify and do all of the nonsense. We verify the cell, test if we test for leaks, we check if it's allocated, and if it is allocated and we do test for leaks, then it means that the data was leaked, memory was leaked, and then we test memory magic word corruption. And of course, if magic word is corrupted, then of course it's a critical error and we can't continue. But if we can continue, ale not owner and magic word corrupted. If neither of those are failing, then previous equal current and current equal next, and status equal max status. Because LOK is 0 and everything else is a number, if we don't have a critical failure, we want to return the error message and not an OK at the end. And then we output the end message after we finish all of this loop and return the status. Init data cell takes the data cell, fills all of the data, and then zero trail. Set memory, just a naive set memory. Get next cell. If the current cell is final, we return a null because you can't get the cell after the final cell. Otherwise, address is the current address, and then we add size of cell and allocation size. Then we return the address as a pointer. Split data cell. If the allocation size in the cell can contain both the allocation and two headers, which one header is for the next header, and the second one is to allow it to have another block, then if we don't have enough size to fragment, we return null. Otherwise, we get the address of the current, then we add the header size and the allocation size to this address, and this address is the next block. Then we init this cell as a new cell with allocation size of the current chunk minus the allocation that we are doing and the header size. So we get the actual data that is going to remain in this cell. Then the allocator address we get from the current cell. This line and this file, because this is a cell that was split from split cell data. So the file is going to be the allocator.c, and you see that the error happened in allocation that happened inside the allocator. And of course, is it allocated? No. Then the current allocation size is the allocation size that we created here, and the current real size is the actual size requested by the user, and then we return the current. Merge cell does basically the same thing, but in reverse, merges the allocation size of this cell with the next cell's allocation size and the size of its header. So basically we reverse the process we had here. The allocation size and real size become that, and we zero the memory inside of the old header to erase it. So we actually force the if we merge two cells and something tries to access a previously merged cell, they wouldn't find a header inside that location. Then we have the zero trail, which basically just if real size is not allocation size, then we get the cell data and skip and go into the allocation size and set it to memory value. Verify cell. Allocator verify was already called, so we just check that the allocator is not null because sanity. Then log file output, magic word, test for magic word in the cell itself, the magic word at the start and the end. Cell address, allocator address. Oh yeah, we already went over this. All of those tests. The real size is not this. Then we do the test 0. Test for memory val. If it's not the memory val, then a memory was overflowed. And now verify allocator, we already went over it. So this is the entire library. This thing is stupidly powerful for stopping dumb mistakes. Instead of copy pasting a project like this, what you should do is make a project like this yourself. The practices that you learn from making this instead of copying and using it is a lot better than just using it. If you just use this, yes, you would stop 90% of your memory related issues in C and C++ and completely nullify pretty much anything Rust developers say about C and C++. You literally have nothing to bitch about if that's the issue. Compilers also already warn you about unused memory, like unused variables. So if I add an int bad unused, it already warns you with unused variable. Bad equal 192. Set but not used. This is actually an output that you would also get not only from in here, but also in your compiler when you try to compile it. And if this another one is uninitialized when used here, so you would get warnings for everything else. And the only thing that isn't caught by the compiler already is this. And this catches basically everything else. Everything that the compiler doesn't catch, this catches. So honestly, just what's the difference between using something like this and using Rust? Nothing. This is why I still use C and C++. They are completely and absolutely perfect languages if you work correctly. They let you work incorrectly because those are languages that are more focused on user freedom than on forcing you to do things in a memory safe way. Because you can fail, you are also more vigilant in testing and in verifying that you use correct logic. If you don't use a correct logic, it doesn't matter how safe your code is. That's the entire thing. And this is the main reason. Also, C and C++ are just easier to use for me. I don't like the syntax of Rust. I don't like the checker and like all of the compile time verification of everything. It's just annoying. I want to use stuff and just test if something failed. Why not test if something failed? Let's go over the macros. Use this macro in your code, please. Use this macro in your code. Nothing is stopping you from using this macro. It fixes so many issues. Just use this. Just use this. Like, nothing stops you from using this. Nothing is stopping you from adding this to your functions to actually have an easier time debugging them. Like, you can see I literally control click and it jumps to the correct line. It literally tells me what variable in my code is causing issues. I don't need to do anything. I don't need to use my brain when I have this. I can use my brain and see that this is bad, but this is just as brain dead as Rust. Like, you just get the results automatically, and you can do it in your own code. It's not hard. Line and file macros let you do that. It's not hard.